Somebody grows tomatoes over a certain period of time and she finds out that the probability of a ripe tomato being big, so having a diameter of 4 centimetres or greater, is 0.3. And then she tests a new fertiliser, and out of a random sample of 30, she finds that 18 have a diameter of 4 centimetres. So 18 out of the 40 are big. So because of this, she claims that the new fertiliser has increased the probability from 0.3. So the first thing that we're going to do this hypothesis test is we're going to define the random variable. So our test statistic, the data that we get, is the number of tomatoes that are greater than 4 centimetres out of a sample of 40. So we know that this random variable is a binomial random variable, and the number of trials is 40, and we're counting how many have a diameter greater than 4 centimetres. So the probability is, let's call it P. So P is the probability of a random tomato having a diameter greater than 4 centimetres. So next we're going to say, well, let's define H0 and H1 actually. So H0 is that the fertiliser has made no difference at all, and that the probability of a random tomato having a big diameter is just 0.3. And our alternative hypothesis is what she's trying to find evidence of, or she's trying to find evidence that the fertilisers increase the probability of a random tomato having a big diameter. So she thinks that the probability now is greater than 0.3 for these 40 tomatoes. So next we're going to say, well, if H0 is true, then we know that X would follow a binomial distribution with 40 trials, and if H0 is true, the probability of a random tomato having a big diameter would be 0.3. So it's worth noting at this point, we would expect, well, the total number of tomatoes that would have a diameter greater than 4 centimetres, if this was the case, would be 30% of 40, 0.3 times 40, which would be 12. So we would only expect 12 to have a big diameter out of the sample of 40, but actually we saw 18. So it seems like there is evidence to suggest, without actually doing the hypothesis test, that the fertiliser may be better. But what we're going to have to do is we're going to have to work out, is that actually statistically significant? Is this in the critical region or not? And at this point, we need to work out what values of X are going to help support our claim. Well, if the probability is increased of a random tomato having a big diameter, large values of X, so a lot of tomatoes out of the 40 having a big diameter, will support H1. And by that, we mean significantly more than the 12 that we would expect. So the preferred method would be to use the p-value method. You would only really ever use the critical region method if the question asks you to find the critical region. So you don't need to draw out the distribution, but I'm going to draw it just to demonstrate what we're actually doing. Draw a quick sketch. So along the horizontal axis, let's put our values of X. So in this case, it's the number of tomatoes with diameter greater than 4 centimetres. And on the vertical axis, we can have the probability. So this is the distribution under H0, i.e. X follows a binomial 40, 0.3. So this is what the distribution would look like if H0 is true. So we could have 0 tomatoes with a big diameter, we could have 1 tomato with a big diameter, 2, etc. Now we're interested in round about 18 because we saw 18 with a big diameter. So it doesn't really matter how we draw this. We could have like 17. The highest probability is going to be around what we'd expect, which is 12, but I'm not going to draw that because we don't need it. And we could go all the way up to 40 because there's a probability associated with all 40 of the tomatoes having a diameter of more than 4 centimetres, although that's going to be really unlikely. So we're at 18. We saw 18 out of the 40 with a big diameter. What we've got to do is we've got to work out, is this in the critical region? Well, because large values of x would support H1, so significantly more than 12, our critical region is going to be the right 5% of the distribution. And it's 5% because 5% is our significance level. So we've got to work out, is this 18, x equals 18, in the right 5% of the distribution? So what we're going to do to determine that is we're going to work out the p-value. So the p-value is going to be, what's the probability where we are or to the right? So that means the probability of x is greater than or equal to 18. And I'm doing greater than or equal to because I know that I need to be in the right of the distribution with large values of x to support H1. So it's a right tail critical region. Well, to work out this probability, we're going to do 1 minus the probability of x being less than or equal to 17. And that's because all the probabilities add up to 1. So we're going to do 1 subtract 0 up to 17. So we'll go on statistics, distribution, binomial, cumulative because we want less than or equal to, and x is going to be 17 because we want less than or equal to 17. Number of trials is 40, and we're entering the probability of H0's true, which is 0.3. And we need to do 1 minus this probability. And if we do that, we'll get 0.0319. So approximately 3.19%. So what that means is this probability of where we are and to the right is 3.1, well, let's round it to 3.2%. So that does mean that we're in the right 5% of the distribution. Because if you think about it, 5% must be something like that. Because this 3.2% has to be within the final 5%. So because the p-value, 3.2%, is less than the significance level, so what that means in this question is 3.2% is less than 5%. We're in the right 5%. So that means that we're in the critical region. So now we need to conclude. So we can reject H0 because we've seen a large enough value of x. 18 was in the critical region, it was big enough. So we're going to write reject H0, and then we need to conclude in context. So we're going to say there's sufficient evidence to suggest that the new fertilizers increase the probability of a tomato having a diameter greater than 4 centimeters. So the key parts in this conclusion are saying what is the p-value and saying that because the p-value is less than 5%, we're rejecting H0, and then saying that we've rejected H0, and then the key words in the conclusion are there's sufficient evidence, and then we've done it in context. So here we've said that it's about tomatoes and the probability of a tomato having a big diameter. Next, let's have a look at the critical region method, and like I said before, I would only recommend doing this if the question actually asks for the critical region. So remember that we're looking for the point at which we've got 5% in the right of the distribution. So because we already know that the probability of x being greater or equal to 18 is 3.2, we know that our critical region has to be at 17 or 16 or 15. So around about there. So let's try the probability of x being greater than or equal to 17. So we'll have to do 1 minus the probability of x being less than or equal to 16. And you should get that as 6.3%. So actually, this is the case, this is too big. So our critical region couldn't include 17 or more, because actually 17 or more would be 6.3%, which is more than the significance level. So that's not going to be our critical region. So next, if we were doing this from scratch, we'd work out what's the probability of x being greater than or equal to 18 to try and make this probability smaller. So not include the 17 bar. And we already know that that's 3.2%. So this is okay, that's too big. So we'd say that our critical region is x is greater than or equal to 18. And that ensures that the probability of being in our critical region when h0 is true is less than 5%. And then we would say that 18, so she saw x is 18. If you go back to the question, she saw that 18 had a diameter greater than or equal to 4 centimeters. So actually we're only just in the critical region, but 18 is in the critical region. So since 18 is in the critical region, so basically we're at this bar here, which is inside the final 5%. We're going to say reject h0, and then we'd make the same conclusion that we made before.